Pattern recognition focuses on a single objective, taking an arbitrary input vector and assigning it to the closest known category. This matching task becomes difficult when the input coordinate sits in the ambiguous space between multiple competing prototypes. Engineers resolve this spatial ambiguity through the specific design of the machine's architecture. This arrangement of processing nodes, weight matrices, and signal pathways is known as the network's topology. Different topologies offer distinct methods for settling spatial conflict, utilizing either static geometric boundaries or dynamic iterative competition. Evaluating how varying structures approach this problem reveals the strict mathematical divide between feed-forward mapping and recurrent dynamics. The formal codification of these models occurred within mid-century research environments like the Massachusetts Institute of Technology. 3 specific architectural challengers emerged to solve the pattern recognition problem: the perceptron, the Hamming network, and the Hopfield network. Early pioneers like Marvin Minsky applied rigorous analysis to these models, defining the mathematical limits of what artificial networks could achieve. Their findings established that a network's architecture dictates its explicit algorithmic capabilities. Analyzing these 3 challengers demonstrates how a network's shape establishes the logic of its internal operations. The perceptron operates as a purely static feed-forward mapping system, processing information in a single pass without internal feedback loops. This abbreviated notation shows the single-layer operation, where A equals hard limb of WP plus B. The weight matrix W and bias B multiply and shift the input vector P to calculate the net input. The hard limb transfer function then acts as a binary threshold on that input, forcing the result to a 1 or a 0. Mathematically, the weight matrix projects orthogonal decision planes that slice the input space into rigid, separate regions. This forces the perceptron to make a decision based on the vector's location relative to a line, rather than its actual distance from a prototype. The perceptron relies on these geometric boundaries, making it ineffective when prototypes cannot be separated by a flat plane. The Hamming network uses a topological structure designed to capture continuous vector similarity. It divides the classification process into 2 distinct stages: detection followed by competition. In this first feed-forward layer, the rows of the weight matrix are populated by the prototype vectors themselves. This matrix product produces a continuous scalar for every potential match, representing the inner product or similarity between the input and each prototype. This first layer functions as a bank of detectors. It identifies the scores, but it cannot yet execute a final classification. By transforming raw coordinates into a spectrum of scores, Layer 1 identifies which prototype is most aligned with the input vector. These similarity scores provide the initial state for Layer 2, a recurrent layer where nodes compete to reach a decision. The layer updates through this recurrent equation. The weight matrix W2 is structured with 1s on the diagonal and negative epsilon values off diagonal. This configuration creates lateral inhibition, a process where nodes actively suppress one another. At each time step, every neuron reduces the strength of its neighbors by a fraction of its own value. As the system iterates, weaker scores decay. The largest value persists while its competitors are reduced to 0. The neuron starting with the highest score uses that lead to drive all other nodes in the layer toward extinction. This achieves a winner-take-all result through dynamic internal pressure, contrasting the static mapping used by the perceptron. The Hopfield network approaches the problem through pure recurrence, removing the feed-forward stage entirely. This topology uses a single, fully interconnected layer where every processing node communicates with every other node. The noisy input vector sets the initial state, and the network then relaxes toward a stable solution. Over several iterations, the chaotic firing patterns settle into a stable equilibrium that corresponds to a stored memory. While the Hamming network uses staged competition, the Hopfield model reaches a decision through the physics of its own energy landscape. Comparing these block diagrams side by side reveals their fundamental topological differences. The perceptron remains limited by the geometry of its decision planes. In contrast, the Hamming and Hopfield models provide flexible classification through recurrent feedback loops. Early engineers implemented these mathematical concepts through dense physical wire meshes. These structures provide the foundational logic for modern neural design. Ultimately, the core principles of metric distance and recurrence scale into the massive, infinitely complex networks utilized today. Mastering the interaction between weight matrices and transfer functions at this scale is a requirement for advanced machine learning. In neural design, topology serves as the primary engineering framework for a system's intelligence.